Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. I have missed you all and it is good to see you again. So before we took our rather impromptu summer break, we were talking about modalities, iterated modalities, affirmative modalities, negative modalities, modalities in standard form, all of these things. In this video, I want to introduce you to more things that we can say about modalities, because the interesting thing with these is comparing them. Which ones imply each other? Which ones are equivalent to each other? And all of these sorts of things. Now, unlike notions of standard form or being affirmative or negative, which are general notions, they hold a modality is affirmative or negative independent of the system that we are looking at. It just depends on how many negations it has. Questions about equivalence and reducibility are going to be system dependent because it's going to depend on what we are able to prove. So when we introduce our first notion in this video, it's going to be the notion of equivalence. But equivalence is always going to be equivalence in a system. So let me just get up our whiteboard. We can start doing some, there we are, some definitions. The first is that of S equivalence, or equivalence in a system. So come on, there we go. Two modalities, and I'm just going to refer, the mouse is not responding as well as I would have liked. I'm just going to call them A and B. So recall that a modality is any string of modal operators and negations, possibly of zero length. But two modalities, A and B, are going to be called equivalent in a system S, if and only if within that system you can prove that if you have one string of modalities attached to a proposition, that if and only if the other string of modalities attached to the proposition. So we can prove in system S that the string of modalities A applied to P, if and only if the string of modalities B applied to P. So the fact that we've got this annotation S here is what indicates that equivalence is with respect to a particular system. So let's just give an example. We know that in system K, necessary P is equivalent to not, possibly not P. So one way to think about this is that this is our first modality A, and this string of 3 is our second modality B. So in system K, and then of course in any system stronger than it, box P, if and only if, not possibly not P. Now, there are other sorts of equivalences that don't hold in system K that might hold in other systems. So one thing that we want to talk about is not only what are equivalents within systems, but if you can end up with, in some sense, shorter or easier to read, easier to understand modalities. So one thing that's really nice about this equivalence is that you might struggle with understanding what does it mean for something to not possibly not be the case. Well, what this equivalence says is you can just think about it as being necessarily the case. So this brings us to a notion of reducibility. So here is our second definition. It says if A and B are equivalent modalities, again, in a particular system, but for the most part, we will just kind of leave reference to the system in the background. You just have to remember that this is a system-specific notion. But if A and B are equivalent modalities, and A has fewer operators than B, so fewer boxes, diamonds, negations, then what we say is that B is reducible to A. So in this case, not possibly not is reducible to just necessarily. And more importantly, if we have one of these equivalencies where one of the two is reducible to the other, then we call that equivalence a modal reduction principle in the particular system that the equivalence holds in. So a modal reduction principle is just the statement of an equivalence. So if we can prove in system S, AP, if and only if BP, where A and B are distinct modalities, and B is reducible to A, then, I got all messed up again. There we go. AP, if and only if BP is a modal reduction principle in system S. And this is a key concept, because what we are going to do now in our attempt to try to be a little bit more systematic about the different modal systems that we are looking at is we are going to take a look at systems and ask ourselves, what are the modal reduction principles that we can prove in this system? So that's one type of question. The other type of question is, here are some modal reduction principles. What happens if I add them to systems that I already have? Take them as axioms. Maybe nothing happens, because maybe you can already prove them in the system. Maybe this is something new, and you end up generating a new system from it. So the idea of having modal reduction principles, equivalent modalities, and we can put these modalities in standard form and all of these things, this gives us a route into looking at different modal systems in a systematic fashion. So there we are. It's lovely to see all of you again. Hope you join me again next time, and we shall talk more about how to do interesting things with modal reduction principles. Until then, take care. Cheers.